My dear student, this is the introductory lecture about the alkalides. What we will learn in this lecture include the basic definition of alkalides, their functions, their nomenclature, classification of alkalides, physical and chemical properties of alkalides, qualitative chemical test for alkalides, isolation and quantitative chemical assay of alkalides. Alkalides, which mean alkali-like substances, are basic nitrogenous compounds of plant or animal origin and generally possessing a marked physiological action on men and animals. Alkalides are a group of naturally occurring chemical compounds that mostly contain basic nitrogen atoms. The term alkalide was coined by Meissner, a German pharmacist, in 1819. Alkalides are cyclic organic compounds containing nitrogen in a negative state of oxidation with limited distribution among living organisms. The nitrogen is usually contained in a heterocyclic ring system and is mainly derived from the amino acids. Alkalides are low molecular weight nitrogenous compounds. About 20% of the plant species have been found to contain alkalides. These are mainly involved in plant defense against herbivores and pathogens. They have also been utilized by the human being. Sometimes alkalides act as growth regulators in certain metabolic systems. They may be utilized as a source of energy in case of deficiency in carbon dioxide assimilation, especially those alkalides containing sugar moiety. Some alkalides are extremely poisonous. For example, ergot alkalides caused epidemic poisoning in the Middle Ages in Europe as a result of feeding on rye bread contaminated with fungus. In the Middle East, the latex of opium poppy papaver was already used in 1200 before the birth of the Christ. Extracts of plants containing poisonous alkalides have long been used as arrow poisons in hunting and warfare purposes. For example, the extract of coraire that contains the tubocorine alkalides have been used to poison the arrows. Certain alkalides have been employed for the execution purposes. For example, in the ancient Greece, Socrates was executed with the hemlock extract, which contains the quinine. At the time of the Roman Empire, belladonna, the source of atropine, has been mixed with the foods with the purpose of murdering. Cleopatra, the queen of Egypt, used Egyptian henna bean that contained hyoscyamine for suicidal purposes. In Egypt, Queen Cleopatra used extracts of henna bean which contain hyoscyamus to expand her purple and appear more attractive to her male political competitors. Certain alkalides are widely used for their psychotropic effects. For example, caffeine acts on the central nervous system as stimulants, and nicotine is responsible for the physiological and physical dependence of the tobacco. There is no hard and fast rule for the nomenclature of alkalides. However, the name of alkalides mostly terminate with the suffix "ine", I-N-E, ine. Their name may be derived from the genus from which it is isolated. For example, atropine is derived from the genus name Atropa. They may also be derived from their species name. For example, cocaine is derived from the species name Coca. They may be named after their common name. For example, ergotamine is derived from the ergot. They may also be named after their physiological activities. For example, amethine is derived from the emetic. There are some alkalides they are named after their discoverer. For example, palliterine is derived from the Paliter, who discovered the palliterine. In addition to the use of suffix "ine", many different types of prefixes are used to name an alkalide. For example, prefix "nor" designate N-demethylation. For example, nor-pseudoephedrine and nor-nicotine. Similarly, apo designates the dehydration. For example, you can see the structure of apomorphine. Similarly, the iso, pseudo, nu, and epi indicates the different types of isomers of the same alkalide. Suffix "dine" represents the dextrorotatory and levorotatory isomers of the same alkalides. For example, cinchona alkalides, as in the case of cinchona alkalides, quinidine and cinchonidine are the optical isomers of quinine and cinchonine respectively. There are many different types of classifications of the alkalides. Some people have used their pharmacological actions for the classifications of alkalides. They have used their biological activities to classify the alkalides. Some others have used their chemical structure. They have emphasized on the presence of nitrogen, either it is present inside or outside of our cyclic ring structure, the number of the ring structures, the type of the ring structures. Some other have used their biosynthetic pathways to classify the alkalides, and hence they have made a biochemical classification of alkalides. Some have used their plant families names and gave the taxonomical classification of the alkalides. Different types of the classification of alkalides. Heegner's classification is based both upon the type of the nitrogen and biochemical origin. Three main types of alkalides according to Heegner's classifications are true alkalides. These alkalides are derived from the amino acids and have nitrogens in their heterocyclic ring. Protoalkalides, these are derived from the amino acids and do not have nitrogen in their heterocyclic ring. The Heegner's classification of the alkalides include the pseudoalkalides. Pseudoalkalides are not derived from the amino acids but have nitrogen in the heterocyclic ring. So the Heegner's classification of the alkalides treats the alkalides into the three types of alkalides: the true alkalides, which are always derived from the amino acids. Their heterocyclic ring contain a nitrogen atom which is derived from the amino acids. The protoalkalides, they are again derived from the amino acids but they don't have any heterocyclic ring. And the pseudoalkalides, these are not derived from any kinds of amino acids and they are still heterocyclic alkalides. Alkalides may be classified on the basis of their pharmacological properties. On the basis of these properties, alkalides may be classified as analgesics. Analgesics are the pain-relieving alkalides. The examples of such alkalides include morphine and codeine. Another class of this group of alkalides include the central nervous system stimulants. The examples of the CNS stimulants include caffeine and strychnine. Class of the pharmacological alkalides include anti-cancer alkalides. The examples of such alkalides include vincristine, vinblastine, and taxols. Another class of the pharmacological alkalides include medrotics. Medrotics are the type of medicine that makes the pupil of the eye to dilate. Medrotics also tend to relax the focusing muscles of the eye, which means that the blurred vision is the common side effect of such drugs. Miotics is another class of the pharmacological alkalides. Miotic drugs also used to increase the pupil of the eye. Miotic works by the contraction of the ciliary muscles, tightening the trabecular meshwork and allowing the increased outflow of the aqueous through traditional pathways. Miosis results from the action of these drugs on the papillary sphincter. The example of anti-asthmatic alkalides include ephedrine. Asthma is a condition in which your airways narrow and swell and produce the extra mucus. This can make the breathing difficult and trigger the coughing, wheezing, and shortness of the breath. Antitussive alkalides include the example of codeine. These are used to treat the cough. Expectorants, these are used to expel out the mucus from the lungs. These include the example of such alkalides include lobeline. Another class of pharmacological alkalides, antihypertensive alkalides. Risperidone is an example to treat the hypertensive patients. Examples of smooth muscle relaxant include atropine and papaverine. Skeletal muscle relaxant include the tubocorine. Examples of anthelmintic drugs include alkalides include palitirine. Anthelmintics are a group of antiparasitic drugs that expels the parasitic worms and other internal parasites from the body by either stunning or killing them and without causing the significant damage to the host. Antiparasitics alkalides include the examples of quinine and amidine. Already told you that the alkalides may also be classified according to the type of their chemical structures. Chemical structures. To this system of classification, alkalides may be classified as heterocyclic alkalides or non-heterocyclic alkalides. Cyclic alkalides are also called as atypical alkalides. These are also sometimes called as prototype alkalides or biological amines. For example, ephedrine, colchicine, and taxose are examples of prototype alkalides or non-heterocyclic alkalides. All these alkalides don't have any kind of nitrogen in their ring. Heterocyclic or typical alkalides is another chemical classification of alkalides which is subdivided into several groups according to their ring structure, pharmacological actions, alkalides are classified according to the amino acid that provides both the nitrogen atom and the fundamental portion of the alkyl skeleton. For example, ornithine provides nitrogen to the pyrrolidine and propane alkalides. Lysine amino acid provides nitrogen and the fundamental portion of the alkylate skeleton to the piperidine, quinolizidine, and indolizidine alkalides. Nicotine provides the nitrogen to the pyridine alkalides. Tyrosine amino acids provide the nitrogen to the phenylethylamines and simple tetrahydroisoquinoline alkalides. Tryptophan amino acid is the responsible for the nitrogen of the simple indole, simple beta carboline, terpenoids, indole, quinoline, and aggregate alkalides. Anthranilic acid is responsible for the nitrogen of the quinozoline, quinoline, and acridine alkalides. Histidine is responsible for the imidazole derivatives. Alkalides may also be classified on the basis of the amino group which they contain. For example, if some alkalides contain the primary amino group, for example, NOR, pseudoephedrine contains the primary amino group. Some other contains the secondary amino group. For example, ephedrine contains the secondary amino group. Nicotine and atropine contain the tertiary amino group, and similarly tubochlorine contains the quaternary ammonium salt of the nitrogen. Now let's discuss some physical properties of the alkalides. Condition. First of all, we will discuss the condition of the alkalide. Most of alkalides are crystalline solids and have sharp melting points. Some are in liquid state, there are other are volatile or non-volatile. The example of the volatile alkalides include nicotine and quinine, whereas the example of the non-volatile alkalides include pilocarpine and hyoscine. Color is another property, physical property of the alkalides. The majority of the alkalides are colorless, but some are colored as well. For example, colchicine and berberine are yellow in color. Optical activity of the alkalides. Many alkalides are optically active. It means that they rotate the plane polarized light either to the right hand or to the left hand due to the presence of one or more asymmetric carbon atoms, which are also called the chiral centers in their molecules. So the majority of the alkalides are asymmetric and have chiral centers, due to which they rotate the plane polarized light and hence show the optical activity. Optical active isomers shows different physiological activities. Usually the levorotatory isomer is more active than the dextrorotatory isomer. For example, levorotatory ephedrine is 3 times more active than the dextrorotatory ephedrine. Similarly, L-ergotamine is 3 times more active than the dextrorotatory ergotamine. There are some exceptions to this rule. For example, dextrorotatory tubochlorine is more active than the corresponding levorotatory form. Both quinine, either levorotatory or its dextrorotatory isomers, quinidines, are equally active. The racemic dextrorotatory and levorotatory atropine is physiologically active as well. Basicity of alkalides is the most fundamental characteristics of the alkalides. The unshared electron pair on the nitrogen atom is responsible for the alkaloidal basicity. Strong basic alkalides can form the salts even with very low weak acids, while weak bases require more acidic media. There are some alkalides that act as amphoteric alkalides, which means they act as acids with bases, and with bases they act as acids. The example of such alkalides include morphine, cyclotrine, and cephaline. The cephaline contains a phenolic group and norcine contains a carboxylic group. Effect of heat and acids on the alkaloidal stability. Alkaloids generally decompose on heating, while some of them sublime. For example, caffeine on heating directly sublime. Cold concentrated acids may cause the dramatic changes, meanwhile heating with dilute acids may cause similar changes. Some alkaloids lose water molecules to form the anhydro or apoalkaloids. For example, morphine on heating is converted into the apomorphine, and atropine is converted into apoatropine. Heating of dilute mineral acids with alkalides may cause the nitrogen or oxygen demethylation of alkalides. For example, quinine, narcotine, codeine, and papaverine show the demethylation upon heating with dilute mineral acids. In addition to the carbon, hydrogen, and nitrogen, most of the alkalides contain oxygen in their molecules. There are few alkalides which contain only nitrogen, hydrogen, and carbon. For example, nicotine and quinine are oxygen-free alkalides. Due to their basic character, alkalides readily form salts with acids. As already told, strong bases form the salts with very weak acids. Weak bases require stronger acids. Dibasic alkalides may form two series of salts. Very weak bases form the unstable salts. For example, piperine, papaverine, narcotine, and caffeine are very weak bases and hence form very unstable salts. Amphoteric alkalides, for example, containing phenolic or carboxylic groups, can form the salts with both acids and alkalis. Alkalides showing acidic characters do not form the salts with acids. For example, racine do not form the salts with the acids. Chemical reduction of alkalides includes Mayer test, Wagner test, Hager test, Dragendorf test, and Merens test. In the Mayer test, potassium mercuric iodide is made to react with the solution containing the alkalides. The majority of the alkalides other than the caffeine and dilute ephedrine give the white creamy precipitate or color. In the Wagner test, iodine or potassium iodide is made to react with alkalides. Upon reacting with alkalides, iodine or potassium iodide give the reddish brown color. In the Hager test, saturated solution of picric acid is made to react with the alkalides and the resulting solution is in yellow color. In Dragendorf test, potassium bismuth iodide react with the alkalides and gave the orange reddish brown color. In Merens test, potassium cadmium iodide react with the alkali solution. If the resulting solution is in yellow color or it gives the yellow precipitates, it indicates the presence of the alkalides. Some other coloring reagents used to detect the alkalides include the Foret's reagent, Madeleine's reagent, Marquis reagent, and Erdmann's reagent. The Foret's reagent includes ammonium molybdate and concentrated sulfuric acids, whereas the Madeleine's reagent consists of ammonium vanadate and concentrated sulfuric acid. Marquis reagent consists of formaldehyde and concentrated sulfuric acid, whereas the Erdmann's reagent consists of concentrated nitric acid and concentrated sulfuric acid. The color formed are characteristics for each reagent. These tests are sensitive to the microamounts of the alkalides and can be used for the colorimetric estimations of the alkalides. This is a simplified extraction plans for the alkalides. First of all, dry the plant, pot in a shadow place, and then powder it. The powder plant material will be extracted with the petroleum ether. The extract will contain the fats, whereas the remaining portions of the plant will contain the defatted powder. It will contain the total alkalides and non-alkaloidal impurities. This non-alkaloidal impurities will be extracted with the alcohol first, and then concentrate the extract, followed by its extraction with the chloroform, and then neutralization with dilute acid. The organic layer, now after the neutralization with the dilute acid, the organic layer will contain the neutral and weakly basic alkalides and other non-alkaloidal impurities. The aqueous layer will contain the salts of strongly basic alkalides. Now the aqueous layer containing the salts of strongly basic alkalides will be neutralized with ammonium hydroxide or sodium carbonate solutions, followed by its extraction with chloroform. The basic aqueous layer will contain the quaternary ammonium bases, whereas the organic layer will contain the basic alkalides. These alkalides may further be separated by column chromatography. There is another plan for the extraction of alkalides called the gradient pH extraction. This method is suitable for the separation of alkalides of different basicity. For example, weakly, moderately, and strongly basic alkalides may be separated with gradient pH extraction method. The crude plant mixture is dissolved in 2% tartaric acid, followed by its extraction with organic solvent. The pH of aqueous solution is gradually increased to pH 9, and the extraction after each increment with the organic solvent. Estimation of alkalides in the given sample of the drugs, galenicals, and pharmaceutical formulation is carried out with the aim of determination of genuineness of the raw vegetable material, evaluation of the plant material for marketing. Quantitative analysis of the alkalides will determine the biosynthesis in the plant, selection of the best stage for the collection of the plant material. It will also help us to evaluate the stability and the activity of the alkalides, prevention and overdose and intoxication of the potent alkalides. It will also help to determine the bioavailability in different organs and tissues. Different methods that can be used for the estimation of the alkalides in the given sample include volumetric methods. These include different types of titrations: aqueous titration, non-aqueous titration, gravimetric methods, colorimetric, and spectrophotometric methods. This is the summary of today's lecture. What we have learned include the definition, basic definition of alkalides, their functions, nomenclature, classification, physical and chemical properties of alkalides, qualitative and chemical tests used to detect the alkalides, isolation of alkalides, quantitative chemical assays of alkalides. Thank you very much.